We learned that in materials, there are three primary bonds: metallic bond, covalent bond, and ionic bond. Atoms are bounded together because of the share or transfer of electrons, resulting in positive and negative ions, like happened in the covalent or ionic bond, or in the case of metallic bond, the sea of electrons model. So the positive and negative ions attract each other to form a bond. Here we are talking about strong attractive forces between the atoms or between the ions. Now the questions are, why solids can hold their shapes if there is a strong attraction? Why don't they collapse because of this strong attraction? Well, to answer those questions, let's first take a look at the bonding forces and energies. Let's see if we have two ions. One is positively charged and one is negatively charged. And we are going to observe the forces between the two particles or two charged ions with respect to the distance between the two particles, which we call interatomic separation. Let's plot the forces between the two ions with as a function of the distance r. The y-axis is the force between the two ions, and the x, or the horizontal axis, is the interatomic separation r, the distance between the two ions. And also we can define the attractive force or attraction and repulsion, the direction of that. So let's say above the x-axis, the positive force is attraction and the negative force is repulsion. And now, when atoms are far away, the distance is very big, they can not nearly see each other, and the forces exerted on each other can be nearly zero. So they do not exert any forces on each other, and they do not have an influence on each other. But when they are brought closer and closer to each other, there will be a pulling force acting on those atoms or ions to pull them closer, since they are opposite charged particles. So if we only consider this attractive force or attraction between the two ions, you can see it increases from zero or almost zero to almost infinitely large, like this, when the interatomic separation distance decreases. So this is what the interaction or the attraction between the two particles look like when we bring them closer and closer. So if this is the only story, we can see when the atoms are getting closer and closer, the attractive force is getting bigger and bigger. So this force is huge that, they will pull the two atoms together, they will overlap, and they will collapse together. But when as the two atoms getting closer, ultimately, the outer electron shells of the two atoms begin to overlap. And the repulsive or a strong repulsive force comes to act. And this is oftentimes explained in terms of Pauli's exclusive principle. So in other words, there's not only an attractive force between the two particles, there is also the repulsive force starting from some distance. For example, here, when the two atoms are closer enough, when the outer shells start to overlap, the repulsive force starts to act. Now let's call it R for repulsion or repulsive. And the net force between the two atoms is just the sum of Fr plus Fa. We use F sub n for net, the total force between the two particles is Fa plus Fr. And let's plot this Fn on this diagram as well. Before the repulsive force starts to play, the net force just equals to the attractive force. So it will just be the same line as this attractive force. And then we need to subtract the value of the repulsive force from the attractive force. So it will look like this. Start to decreasing. And this is the curve for the net force. Now we can see at some distance, the net force between the two particles is 0. F equals to 0. And we call this distance R naught or R0. And we call it the equilibrium inner atomic separation distance. Because at that point, at R0 here, the distance or the forces is 0, so the two particles are at equilibrium. So from the curve of the net force, we can see that as two atoms approach one another, they at first experience attraction. They repel each other when they are brought very close. At R equal to R0, the net force is 0. Let's recap on what we just learned about the bonding forces between two isolated atoms. When the atoms are at large interatomic separation distance, we use letter R for that. The atoms do not exert any forces on each other because they're too far away. But when the distance R decreases, an attractive force Fa starts to act and is getting bigger and bigger to pull the two atoms closer. And the relation between this attractive force Fa and the distance R is given by this following formula, where Fa equals to A over R squared. And this value A can be calculated from the properties of the two ions. Z1 times Z2 times E squared over 4 pi epsilon 0, where Z1 and Z2 are the valences of the two ions respectively. So when you do the calculation, we use the number, absolute number of the valences for each atoms, so do not carry the positive or negative sign. E is the electronic charge, which is a constant given here, and epsilon 0 is the permittivity of vacuum, which is also a constant value. So you can use this value directly in your calculation. As the atoms getting closer, starting from certain distance, the repulsive force F sub R began to act. The net force Fn between the two atoms is given by Fn equals to Fa plus Fr. So in this case, we defined we use the sign convention. Attractive force is positive and repulsive force is negative. So Fr, when you substitute in this equation, should be a negative value. At some interatomic distance R0, Fr exactly equals to Fa, but they are of the opposite directions, so the net force between the two atoms becomes 0. So that's the equilibrium position of the two atoms, and this R0 refers to as the equilibrium interatomic separation distance. Sometimes it's more convenient to use the bonding energy or the potential energy between the two atoms instead of using the forces. Mathematically, we know that E, the energy, equals to force times the distance. So if force is a variable, then E equals to the integration of force times dr. And force is the force at the given r. Or we can rewrite this equation. So force equals to the derivative of E over r. which means the force value at a given location R, for example here, this value F is the slope of the energy curve at the same R. So based on this relation, we can plot the bonding energy between the two atoms versus the interatomic separation R. So I'm going to give the graph to you directly. Same idea, we have the repulsive energy and attractive energy. Add them together, we'll have the net energy between the two atoms. So here we set the positive value to be the repulsion energy, and the negative one is the attraction energy. So this is just a sign convention. We made the sign. You can flip the directions of the two energies, okay? Because what really matters is the magnitude of the energy. All right. So now, if we take a closer look at this plot, since we know F, the force, is the slope of the energy curve. When the slope equals to 0, meaning when R equals to R0, we know that Fn, the net force, equals to 0. So a zero slope means a inflection point, which corresponds to either a minimum value or a maximum value on the energy curve. So in this case, R equal to 0 means the energy is at a minimum value. So at R0, which is the equilibrium interatomic separation distance, R0, the net force between the two atoms is 0, and the energy between the two atoms is at its minimum value. So this is the minimum value required to break the bond between the two atoms. We can calculate the value of the bonding energies using the following formulas. The attractive energy E sub A, by the sign convention, if we're going to plot this E sub A on the same diagram as E sub R, it is a negative value. Therefore, we need to use the negative sign in this formula. It's negative A over R, where A is a constant, depends on the bonding type and the atoms being bonded. So it's a property. And repulsive energy E sub R is a positive energy based on the sign convention, and ER equals to B over R to the power of N, where B and N both are constants as well, will be given when you have certain materials. So the net energy E sub N is the sum of the attractive energy and the repulsive energy. So again, R is the interatomic distance or interatomic separation distance between the two atoms. A and B and N are constants, which depend on the bonding types. And if we have a problem to solve, the value of A and B and N will be given. For most ionic bonding, we use 8 for the N. Now let's see how can we use the bonding energy diagram to predict the properties of the material. First, let's take a look at the melting point of the material and how is that related to the bonding energy. So here again is the bonding energy versus the interatomic distance R, and R0 is the equilibrium interatomic distance. So atoms are vibrating at their equilibrium positions, right? At room temperature, for example. Even though we see the solid, we see a piece of metal hold its shape, but atoms are at vibration all the time. Assume now the temperature is at absolute zero. 0 Kelvin. So at 0 Kelvin, all the atoms are kind of freezed. Okay, it doesn't move. So the interatomic distance will be R0. Now when we raise the temperature a little bit, so the atoms start to vibrating at their positions. So you can assume, you can imagine those atoms are like balls rocking at the bottom of this well. So sometimes we refer to this part as the energy well. It looks like a well, right? So again, if we raise the temperature a little bit, the atoms start to vibrating, and raise the temperature higher, it vibrating more and more and more until it breaks the bond. And remember, we mentioned the minimum energy to break the bond is E0. So that means to melt the solid, we have to overcome this energy well to overcome the E0 to break the bond. In other words, the bigger value of E0, the higher temperature we need to break the bond, meaning the higher temperature to melt the material. So the material will have a higher melting point. So now if we compare, or if we are given the energy curve of two materials, so this is material A and this is material B. Well, apparently material B has a deeper energy well, which means the E0B is bigger than E0A. So material B requires more energy to break the bond, to melt the material, so it has larger melting point. So we can say the melting point is larger when E0 is larger. Another material property we can predict from the energy R plot or curve is the coefficient of thermal expansion, alpha. So we all have the experience that when temperature increases, most material will expand, which means the dimension will be larger. For example, wood or some other type of materials, when you heat it up, it will expand. And this alpha term is defined as the fractional change in linear dimension or in dimension of the material per degree of temperature. So here is one example. If we have a piece of metal, before we heat it at temperature T1, it has a length L0. But when we increase the temperature to T2, it will expand and the length will increase to another length, and the change is delta L. So this alpha is defined by delta L over the original dimension. So this is the fractional change. It equals to alpha times the change in temperature. So this is how the coefficient of thermal expansion, alpha, defined. The coefficient of thermal expansion alpha is related to the asymmetry of the energy R or energy separation curve, or is related to actually the shape of the curve. So think about how to change the dimension of the material, or what does the change of the dimension means? Well, if we can increase the interatomic distance, for example, originally this is the distance between the two atoms, and if we can increase the distance between the atoms, the overall dimension of the material will also increase. which means the increase of the average interatomic distance corresponds to the overall increase in the dimension of the material. So for this asymmetric energy separation curve, when we increase the temperature, so again, at the bottom here is K or T equals to 0. Everything is phrased at this position. But when we increase the temperature, the atoms start to vibrate. So that's the distance. Average distance between the two atoms is R1. And E1 is the thermal energy we provided to the material, which corresponds to a T1. T1 is a relatively low temperature. Now we increase the temperature to T2. We provide this material with a higher thermal energy, E2, and the vibration will be more. And the average temperature or average distance between the two atoms becomes R2. And we increase this even more to T3. And now the average distance, which is the midpoint between these two endpoints here, becomes R3. And so far so on until we increase the temperature to T5. And now the average interatomic distance between the atoms are R5. Now you can see when we increase the temperature from T1 all the way to T5, where T1 is less than T5. Now, the interatomic distance increases from R1 all the way to R5, which means the average equilibrium separation between the atoms increases and the material will expand. So in summary, this is a relatively asymmetric curve. When we increase the temperature, the average interatomic separation will increase from R1 to R5, and that corresponds to thermal expansion, meaning alpha is relatively larger. Now if we compare to a curve that is symmetric, so this is totally symmetric. Now, even if we increase the temperature from T1 to T2, then to T3, because it's symmetric, now the midpoint is always at the same value. So that means no matter how we increase the temperature, then the distance, average distance between the two atoms doesn't change. That means the dimension of the material doesn't change as much as a curve as an asymmetric curve. So that means for a symmetric curve, when we increase the temperature, no increase in average interatomic separation. That means there's no thermal expansion. Now we know the coefficient of thermal expansion alpha is related to the shape or asymmetry of the ER curve. But after doing a lot of studies, doing a lot of researches on all types of materials, by plotting this ER curve, we have a conclusion where for each class of materials, including metals, ceramics, and polymers, the greater the atomic bonding energy, means the larger the E0 is, the deeper and narrower the potential energy well is. As a result, the increase on interatomic separation with given rise in temperature will be lower, meaning for the deeper and narrower energy well, the increase on the separation will be smaller because it's narrower, which yielding a smaller value of alpha. So make it simpler. We can say when E0 is smaller, then alpha is larger. Or when E0 is larger, the alpha is smaller. Again, the deeper, the narrower. The narrower, the more symmetric it is. That means alpha is smaller. So that means instead of checking the shape of the curve, we can just use this conclusion, just check the E0 value, the bonding energy. The smaller the bonding energy, the larger the coefficient of thermal expansion. Let's compare the properties of different materials having different bonds. So for ceramics, usually it has ionic bonds. So ionic bond has the highest bonding energy, so which corresponds to a large melt point and a large, this is the modulus of elasticity, which we'll learn in chapter 6, and corresponds to the stiffness of the material, and smaller thermal expansion coefficient. For metals, which has metallic bonds, it has variable bond energy, so the melting temperature is moderate compared to ceramics and polymers, and moderate elasticity, and also moderate alpha coefficient of thermal expansion. Polymers usually has covalent bonds or secondary bonds, so the bonding energy is relatively low. Therefore, the melting point is also smaller, and it has a smaller elasticity, but it has a large thermal expansion coefficient. So in this lecture, we focused on the bonding energy and bonding forces between the atoms. And also we explored the relation between the bonding forces and bonding energies with respect to the interatomic distance. So we should know that energy at the equilibrium position, or 0, is at its minimum value, whereas force at equilibrium position is 0. Always keep in mind that when we mention equilibrium position, the net force is 0. Larger depths of the energy well, meaning the larger bonding energy, means higher melting point and stronger material. Smaller bonding energy means a larger thermal expansion coefficient, alpha.